Hello friends, welcome back to the channel. In continuation of our last video on RBAC, today we are going to see how to use cluster based role binding using a service account. So today we will understand what is a service account, why we need a service account in Kubernetes, how do we create it, and how to provide cluster level permissions using ClusterRole and ClusterRoleBinding. In the last video, we understood that in Kubernetes, role and role binding are namespace scoped resources. This means the permissions granted to a user or a service account are limited only to a namespace where the role binding is created. For example, if a user has access to pods in dev namespace through a role binding, that user will not be able to access resources in prod namespace unless additional permissions are provided there. So we can use role and role binding for namespace scoped resources like pods, deployments, replica sets, services, etc. We can provide permissions like get, list, watch, create, update, delete, and edit for these resources. But when there are multiple namespaces, creating separate roles and role bindings in every namespace becomes repetitive and difficult to manage. Also, when we need to monitor or access cluster-wide resources like nodes, node metrics, persistent volumes, namespaces, etc., we cannot use role and role binding because these are cluster scoped resources. To solve this problem, Kubernetes provides cluster role and cluster role binding. Cluster role defines permissions at the cluster level, and cluster role binding assigns those permissions to users, groups, or service accounts across the entire cluster. However, according to the principle of least privilege, we should always prefer using role and role binding whenever namespace level access is sufficient, and use cluster role and cluster role binding only when cluster wide access is actually required. Well, in the last video, we attached a role and performed a role binding to a user. Now the question is, what types of users do we actually have in Kubernetes? Basically, we have two types of users in Kubernetes. The first type is human users like employees, developers, DevOps engineers, or administrators who are trying to log into the Kubernetes cluster and perform operations. The second type is service accounts. So what exactly is a service account? A service account is something that applications use to interact with the Kubernetes cluster. Now think about this real-time scenario. Suppose an application like Jenkins, a Spring Boot application, or a Python application wants to access Kubernetes resources through the API server. Can we directly use our organization email ID and password inside the Jenkins or inside these applications? The answer is no. That is not secure, and it can also become a major audit and a security issue because we should never expose human credentials inside applications. That's exactly why Kubernetes provides service accounts. Service accounts are special types of users meant specifically for applications. You can think of them as application identities or application users inside Kubernetes. Whenever a namespace gets created, Kubernetes automatically creates a default service account inside that namespace. You can verify that using kubectl get SA. Here SA is the short form of service account. As you can see, a default service account is already present. Now the pods where our applications run use these service accounts to authenticate themselves with the Kubernetes API server. And if we do not explicitly mention which service account to use, the pod will automatically use the default service account of that namespace. Now let's understand this complete flow of using cluster role binding and service account with a real-time scenario. Suppose we want to monitor our Kubernetes cluster nodes and collect metrics such as CPU utilization, memory usage, file system usage, and other node level metrics. And we are using Prometheus for monitoring. Now this monitoring application needs to connect to Kubernetes cluster and retrieve metrics related to node resources. As we already know, whenever any request reaches to Kubernetes API server, Kubernetes first performs authentication and authorization, and only after that the requested action is allowed inside the cluster. Similarly, When this Prometheus or any monitoring application tries to access the Kubernetes resources, it also has to go through these two steps, authentication and authorization. First comes authentication. Now the question is, how will this application authenticate itself with Kubernetes? For that, we create a service account. In a simple way, you can think of service account as a user identity for the application, and the service account token as the credential used by the application to authenticate with the Kubernetes API server. Whenever a pod uses a service account, Kubernetes automatically mounts the token inside the pod, and the application uses that token to communicate securely with the API server. Once authentication is successful, the next step is authorization. Authorization simply means what actions is the application allowed to perform and on which resources. Now, in our case, the monitoring application needs access to node metrics, but node metrics are cluster scoped resources in Kubernetes. That means namespace level role and role binding are not sufficient here because they work only within a particular namespace. Since we need cluster-wide access, we use ClusterRole to define cluster level permissions and ClusterRole binding to attach those permissions to the service account. So the complete flow is Prometheus application runs inside a pod. The pod uses a service account. The service account token authenticates with the Kubernetes API server. ClusterRole defines what resources can be accessed. ClusterRole binding connects the service account with those permissions. And finally, the monitoring application is able to retrieve node metrics from the cluster. This is the most common real-time use cases of service account, ClusterRole and ClusterRole binding in Kubernetes. So let's start with the hands-on demo. In this demo, we will implement Kubernetes RBAC for a real-time monitoring use case using Prometheus and a Node Exporter. We will create a service account for secure authentication with the Kubernetes API server, and its token will automatically be mounted into the pod. Since Prometheus requires access to cluster scoped resources like nodes and the metrics endpoints, namespace level role and role binding are not sufficient. Therefore, we will use ClusterRole and ClusterRoleBinding to provide cluster-wide read access. And Node Exporter will be deployed as a DaemonSet so that one exporter pod runs on every node and exposes node level metrics for Prometheus scripting. Well, before starting the demo, let me show you my Kubernetes cluster. Here we have one master node and two worker nodes. So our cluster is up and running. Now let's check which namespace we are currently working in. For that, we will use kubectl config view --minify pipegrep namespace. So currently we are in the default namespace. Now let's create a simple pod using the imperative command. For that, we will use kubectl run. The pod name is demo pod and the image we are going to use is nginx. Hit enter. Now verify kubectl get pods demo pod is running. Once the pod is running, let's inspect it using kubectl describe command. Kubectl describe pod and then pod name. Hit enter. In the output, you will see details like namespace, name of the pod, service account, etc. And here is the important part. You will see service account default. This means whenever a pod is created, Kubernetes automatically attaches a service account to it. So basically, every namespace has a default service account, and if we don't specify anything, the pod uses this default service account. And this allows the pod to communicate with the Kubernetes API server. Now let's check the service account. For that, we can run the command kubectl get SA. Here SA means service account. If we check all namespaces using kubectl get SA-A, so here you will see multiple service accounts across all namespaces. like default, envoy gateway, queue, flannel, and these are the default service accounts available. So every namespace has its own default service account. Now let's go back to our pod using kubectl describe pod name. So here scroll to volumes or mount section. Here you will see something like /var/run/secrets kubernetes.io service account. This is where Kubernetes automatically mounts the service account credentials. Now let's go inside the pod using kubectl exec-it and the pod name --sh. So here inside the pod, so here do ls-lart to var/run/secrets/kubernetes.io/service account and hit enter. Here you will see three files. One is ca.crt, another one is namespace, and the next one is token. So now let's check the token. For that, get to this token, hit enter. You will see a long JWT token. Now copy this token, open jwt.io in your browser, paste it in the encoded section here. So here under decoded payload, you will see decoded information like namespace, node name, pod name, service account, expiration time, issue time, etc. So a single token contains identity of the pod, namespace, service account details, authentication metadata, etc. So in our lab, we will see a complete end-to-end Kubernetes RBAC demo using service account, secret, ClusterRole, ClusterRoleBinding, node exporter, and access verification. So let me take you to the IDE. So here under the day17 folder, we have the observability framework directory. In our day17 session, we already saw how to deploy Prometheus Node Exporter as a daemon set to collect node level metrics from the Kubernetes cluster, and we deployed it in the default namespace. Let me quickly walk you through these manifest. So here under node exporter DaemonSet.yaml, we are creating a daemon set. As we already know, a daemon set ensures that one pod runs on every node. Why are we using daemon set here? Because node exporter is responsible for collecting node level metrics like CPU usage, memory utilization, file usage, and network statistics. So every node should run on node exporter pod. That's why daemon set is the perfect choice here. Inside the container section, we are using image, that is prom node exporter latest, means we are using the official node exporter image here. So if you observe carefully, we are mounting /sys/proc from the host machine into the container. Why? Because node exporter needs access to the actual host level system metrics from the node. For example, /proc contains process and CPU information, /sys contains kernel and device information, and this root file system contains disk related metrics. Without these mounts, node exporter cannot read node level metrics properly. We have also created this node exporter service.yaml. So here we are creating a Kubernetes service. Now the question is, why do we need a service? Because node exporter exposes metrics on 9100 port number. Prometheus needs a stable endpoint to scrape these metrics. So pods are dynamic in Kubernetes, means pod IPs can change, pods can restart, pods can get recreated. So instead of directly accessing pod IPs, we create a service which provides a stable internal endpoint for Prometheus. So here we are using cluster IP type of service, means the service is accessible only inside the cluster, which is completely fine because Prometheus is also running inside the cluster. So using these manifests, we have already deployed the DaemonSet in our Kubernetes cluster. So if in our cluster, if I run kubectl get DaemonSet -o void, hit enter. So here you will see SEH Node Exporter DaemonSet is running. As we already know, DaemonSet runs one pod per node, and currently we have two worker nodes, worker 1 and worker 2. So Kubernetes automatically created two node exporter pods. Now if I check the pods using kubectl get pods, so here you can clearly see one pod is running on worker node 1. If I do kubectl get pods -o void, so here one node exporter pod is running on worker node 1 and the another one is running on worker node 2. This confirms that our DaemonSet is working correctly. Now currently these pods are using the default service account. So in the next step, we will create our own custom service account and attach cluster role permissions and bind it using ClusterRoleBinding, and finally then verify how authentication and authorization work internally in Kubernetes. Now let's create a service account. Well, there are two ways to create Kubernetes resources. One is imperative way, means using commands, and another one is declarative way, using YAML manifest. I will show you both approaches. So to create a service account using command, we use kubectl create SA and then service account name. Here SA stands for service account. Hit enter. Test SA created. Now validate using kubectl get SA. You can see service account has been created. Now let's create the same thing using YAML manifest, which is recommended approach in real-time project because it supports version control, automation, GitOps, and easier management. Let's go back to the IDE. So here under the day18 folder, we will create manifest for service account, secret, cluster role, and ClusterRoleBinding. Let's start by creating service account.yaml. Here again, we will need to specify API version, that is v1 for service account, kind service account only, metadata. Here we will provide the name of the service account. Name, let's give it SEH Node Exporter SA. It's a very simple manifest. Here kind service account tells Kubernetes to create a service account, and SEH Node Exporter SA is the name of the service account. So we are not explicitly mentioning any namespace. This service account will be created in the default namespace. Now let's create a secret for the type service account token. Create a new file, secret.yaml. Again here API version, that is v1 for secret, and kind is secret only, and then metadata. Here provide the name of the secret, that will be SEH Node Exporter token. So here we will use annotation. Annotation kubernetes.io service account.name. This annotation is to attach this token to the service account, that is SEH Node Exporter SA, which we have just created. So here type Kubernetes.io service account token tells Kubernetes that this secret should store a service account token, and this annotation is very important. This links the token secret with our service account. Once this secret gets created, Kubernetes automatically generates a token and associates it with the service account. This token can then be used by application to authenticate with the Kubernetes API server. Now save the changes. Since I am using GitHub as my version control system, let's commit the changes to the GitHub repository. For that, we will use git commands like git add dot, git commit -m, then commit message, and git push. Now on my Kubernetes cluster machine, I have already cloned the Kubernetes playlist repository under /opt/code repo, and I am already inside the directory that is Kubernetes playlist. Now let's pull the latest changes using git pull command. Now if I go inside day18, cd day18, here I can see both files are available now. Now let's apply these files using kubectl apply command. First create a service account, so use kubectl apply -f serviceaccount.yaml. Hit enter. You will see service account and then service account name created. Now create the secret using kubectl apply -f then the secret manifest file name. Hit enter. You will see secret and then secret name created. Now let's verify. Check service accounts using kubectl get service account. Here we can see our newly added service account is available here. And then check secrets using kubectl get secret command. And here we can see SEH Node Exporter token, which we have created 20 seconds ago. Now you can see our custom service account and the token secret associated with it. So till now we created a custom service account, generated a token secret, and prepared the authentication part of our monitoring application. Next we will configure authorization using ClusterRole and ClusterRoleBinding. Now let's go back to the IDE again and start preparing the ClusterRole and ClusterRoleBinding manifest file. First, let's create a new file under the day18 directory. Touch, then ClusterRole.yaml. Now we will start with the API version. If we are not sure about the API version or resource type, we can always verify it directly from the Kubernetes cluster. And the command is kubectl API-resources pipe grep then resource name. Hit enter. Here we can see both ClusterRole and ClusterRoleBinding belong to the same API group. So now let's start writing the manifest file and provide the API version as rbac.authorizations.kubernetes.io/v1, and here kind is ClusterRole. Next comes the metadata section. Here we provide the name of the cluster role, Prometheus cluster role. Now this is a very important part. In most Kubernetes manifest we usually define a spec section, but for RBAC resources like role and a cluster role, instead of spec we define rules. So now write rules, because here we are defining what resources can be accessed and what actions can be performed on those resources. So let's start with the rules section. Now inside rules, the first field is API groups. Now what exactly is API groups? Every Kubernetes resource belongs to an API group. For example, pods use API version as v1. Service use API version as v1. See here, pod uses API version v1. Since they belong to the core Kubernetes API group, we leave API groups empty using double quotes. But if we compare that with deployments, let me show you deploy.yaml as well. So for deployments, we use API version as app/v1. So here the API group is apps. If we were defining permissions for deployments, we would write API groups as apps here. But in our case, we are defining permissions for pods, nodes, services, endpoints, and nodes or proxy, which belong to the core API group, so we leave it blank. Next comes the resources section. So here we define on which Kubernetes resources this cluster role should provide access. For example, nodes, access node information, node/proxy, access kubelet, metrics, and node proxy endpoints, services, discover services, endpoints, discover application endpoints, pods, discover running pods. These permissions are commonly required by monitoring tools like Prometheus. Now next comes verbs. Verb simply means what actions are allowed on these resources. For example, get, list, watch. Get means retrieve the specific resource. List means list all resources. Watch means continuously monitor changes in resources. For monitoring tools, these three permissions are usually sufficient because Prometheus only needs read-only access. Now similarly, we can define multiple rules. For example, here we are defining read access to config maps. Prometheus may use config maps for storing configurations, scrape targets, or monitoring related things. Now the next section is very important and often confusing. So normally RBAC works with Kubernetes resources like pods, nodes, services, etc. But some endpoints exposed by the Kubernetes API server are not actual Kubernetes resources. For example, /metrics. This endpoint exposes Kubernetes and a cluster metrics. Since /metrics is a URL endpoint and not a Kubernetes object, we use non-resource URLs and allow the get action on it. So here is our complete manifest file for the cluster role. Now let's create the next file, that is ClusterRoleBinding. As we discussed earlier, cluster role only defines the permissions, but Kubernetes still does not know who should use these permissions. That is exactly where ClusterRoleBinding comes into the picture. ClusterRoleBinding connects or binds a user, a group, or service account with a cluster role. So let's start writing the manifest file line by line. First define the API version. Again, this belongs to the RBAC API group. Next, define the kind. ClusterRoleBinding. Here we are creating a ClusterRoleBinding resource. Now comes metadata. This is simply the name of our ClusterRoleBinding object, that is Prometheus ClusterRoleBinding. Now comes the most important section, that is subjects. Now let's understand this carefully. Subjects defines who should receive these permissions. In our case, we want to provide permissions to a service account. So we define kind as service account here. Then name, this should be the exact service account name that we created earlier. Let's copy the service account name from here and paste it here. And very important, namespace. Let's make it default. Because service accounts are namespace scoped resources, Kubernetes must know from which namespace this service account belongs. Now next comes role ref. Role ref, this section defines which role should be attached to this service account. So here kind is cluster role, means we are attaching a cluster role. Name is Prometheus cluster role. Prometheus -cluster -role. Let me copy this and paste it here. Is the cluster role we created earlier. And API group, the API group again belongs to RBAC, RBAC.authorization.kubernetes.io. So basically this cluster role binding is acting like a connector between service account and a cluster role. Now once we save this file, commit the changes to GitHub using git commands. Once it is done, on the Kubernetes cluster, do git pull to pull the latest changes in the Kubernetes server. Now cd to day18 folder and here apply the manifest one by one. Now before applying, let's quickly understand the complete flow in one line. The pod uses the service account for authentication. The service account token is automatically mounted inside the pod. Cluster role defines cluster-wide permissions. Cluster role binding attaches those permissions to the service account. Node exporter runs on every node using DaemonSet, and the Prometheus accesses the metrics exposed through the node exporter service. Now let's apply the resources one by one. First apply the cluster role using kubectl apply -f clusterrole.yaml. Next apply the cluster role binding using kubectl apply -f clusterrolebinding.yaml. We already have DaemonSet ready and we have already created our service account. Now let's validate everything one by one. First check service accounts using kubectl get service account. So we have SEH node exporter service account available here. Next check cluster roles using kubectl get cluster role command. So our Prometheus cluster role is available here. That was created today itself. Then check cluster role binding using kubectl get cluster role binding command. Here our Prometheus cluster role binding is available. That is created 74 seconds ago. Now check DaemonSet using kubectl get DaemonSet command. So we have SEH node exporter DaemonSet available. Check pods running on the nodes using kubectl get pods command. So here SEH node exporter pods are running. If we do kubectl get pods -o wide, you will be able to see one pod running on every node because DaemonSet ensures one pod per node. So SEH node exporter pod running on worker node 1, the same way this one is running on worker node 2. Now let's verify whether the service account actually has permissions to access cluster level resources. For that we will run kubectl auth can I list nodes as service account. Our namespace is default, so provide the default namespace here. If everything is correct, you will see the output as yes. Now let's verify whether the token is mounted inside the pod. So first get the pod name. So here we can see ca.crt, namespace and token, all these are available. This confirms that Kubernetes automatically mounted the service account token inside the pod. Now finally, let's access this matrix exposed by node exporter. For that we will use port forward. First of all, exit from this pod and run the kubectl port forward command. Now on the another tab, now let's finally access the metrics exposed by Node Exporter. I have already exposed the service on port 9100, and now if I run curl http:/localhost:9100/metrics, you can see a huge list of metrics being exposed. Now don't worry if this output looks like confusing initially. These are Prometheus format metrics, and this is exactly what Prometheus scrapes internally. Here you can clearly see different types of node level metrics. These metrics are related to network usage. Node network receive, no handler total, packets total, transmit carrier total, bytes total. These provide information about how much data is being received and how much data is being transmitted throughout the network interface. Similarly, here we can see CPU related metrics: node scrape collector, duration seconds, collector, CPU. And memory related metrics: go, memstats, alloc bytes, etc. We can also see file system related metrics and many other node statistics being exposed. So basically, Node Exporter is collecting all these node level metrics from the Linux host and exposing them on the /metrics endpoint. And Prometheus continuously scrapes these metrics for monitoring and alerting purposes. This is how complete flow works. Application authenticates using ServiceAccount. Authorization is handled using ClusterRole and ClusterRoleBinding. Node Exporter runs on every node using DaemonSet. And Prometheus collects all these metrics for monitoring the Kubernetes cluster. So in this video, we understood what service accounts are, why applications should use service accounts instead of human credentials, the difference between role binding and cluster role binding, why cluster role is required for cluster scope resources, how authentication and authorization work in Kubernetes, and finally how Prometheus and a Node Exporter use RBAC to access cluster metrics. Well, that's all for today's session. You will find all the manifest files in the GitHub repository. I will share the GitHub URL in the description box. If you found this video helpful, hit the like button, share it with your friends, and don't forget to subscribe to the channel. Thanks for watching and happy learning.